Okay, now we have to continue with our fast resume. Sorry. Dongiovanni is asking you to stay here. You can go out. It's not a problem. Okay? So, the resume of the first law of thermodynamics. Yesterday we wrote 3 fundamental relationships that we will continue to use in our course, that are the first law, in order to remember, first law of thermodynamics, in Lagrangian forms, means for all closed system, and remember, we have no restriction when we have to apply this relationship. But we wrote also this for open system, but in order to have this formulation we need an additional restriction, one restriction: the flux, the system has to be in steady state. Otherwise, we cannot apply this relationship. At the same time, we wrote also the conservation law for the energy in a mechanical form. And with the reference to the Lagrangian approach, closed system, we wrote relationships of this type. C or K stand for kinetic, with the friction work, because when we separe the energy from the thermal state to the mechanical state, we have to introduce the conjunction between them, that is the friction work. And this relationship is always true, no restriction. At the same time, we can write a similar relationship for open system with reference to the technical work, the work done through shaft, through moving components in our machine. Where always we have the restriction of steady state. By combining this relationship, we obtained also another very interesting relationship that say that the total amount of heat received by our system, closed or open, doesn't mind, is equal to the variation of internal energy plus P dV, that by applying the definition of enthalpy, remember enthalpy is defined like the internal energy plus PV, can be also written like dH minus V dP. And also this relationship is always true, no restriction for it. These are the relationships that we wrote yesterday. Well, These particular relationships, the conservation of energy in the mechanical form, can be written by adding other restriction in another popular way, that is the Bernoulli theorem. The Bernoulli theorem, we write the energy conservation, but we write the energy with reference to the unit of weight of our fluid. So, energy for unit of weight. The unit of measurement is energy? Joule. Okay. The unit of measurement for weight? What is? No. The unit of measurement for the weight. Weight. Newton is a force. Newton. Therefore, do you remember that how the Joule is connected to Newton, etc.? The relationship is work equal to force time displacement. Therefore, Newton time meters over Newton. Therefore, this unit of measurement becomes meter. Okay. No, but it is an energy. Energy refers to the unit of measurements of the weight for each Newton of fluid. This is why we measure the energy in this particular form like an 8. Okay? And if you remember, when you write the Bernoulli relationship, the Bernoulli theorem, you write this energy conservation with reference to some restriction. Do you remember the restriction? When the Bernoulli theorem is valid, there are a series of restrictions. First of all, the fluid has to be incompressible. Good. So, constant. Another? Better than no viscosity is correct, but usually we say ideal. Ideal means no LW, no viscosity. Ideal. Then, do you have other restriction? The flow has to be? Oh, absolutely. Doesn't mind. It's ideal. It cannot be laminar, turbulence. It's an ideal fluid, no viscosity. Reynolds number cannot be defined. The flow has to be the steady? In steady state condition. Oh, there is another one, another hypothesis. When you apply the Bernoulli relationship, like in the past, do you have changement or introduction of energy in the middle of subtraction? In other words, do you have a machine that works on the fluid, or you only have a pipe or fluids that moves without pump or turbine? There is no machines applied. So no machines means then the Li is equal to 0, no rotational shaft. There is another hypothesis, but no one remembers. The flux has to be a particular type of flux, irrotational, not rotational. It means that the rotor of the velocity has to be equal to 0, but more simply, it means that if you look at a molecular mass of your fluids, this mass is only able to move without rotating. So there is not a rotation of your mass. The mass in your pipe moves in this way, not in this. Okay? So by applying all this restriction to this relationship, we obtain del I equal to 0. 0. V dp is obviously V dp, or by integrating, dp is the variation of delta p, V is constant, therefore delta p over rho. Kinetic energy plus c square over 2. Gravitational energy plus gz. Omega, no rotation, equal to 0. LW, ideal, equal to 0. So this is the conservation of energy, of mechanical energy, in the mechanical form, written under this hypothesis. By dividing by G, you obtain, I have to put here delta and delta also. You obtain the usual form of the Bernoulli equation that say that the head, that we call with H with a O at upstream, is equal to Z plus P over gamma plus C square over 2G is constant. This is the Bernoulli relationship. But we can use, instead of the Bernoulli relationship, these relationships when we have to work with machines, when our fluid is not ideal. So we can also call this relationship like an extension, a generalized Bernoulli equation. It's without a lot of restriction. Okay? But remember, when in the past you used the Bernoulli's equation, now we can do the same things. We use this relationship that is approximately the same. It's the same things. So the study you did in the past can be applied, or the consideration you did in the past can be used also today, also in our machine. When we work with a liquid, usually we wrote the Bernoulli's equation or the conservation of energy in mechanical form. They are identical. Okay? So these are the, let me say, the most important things that we have to remember about the first law of thermodynamics, the energy conservation. Okay? Equation. Now, we have to write something also for the second law of thermodynamics. Okay? Do you remember the formulation that my colleague gave for the second law of thermodynamics? First of all, they introduced a new thermodynamic properties. Okay, that is the entropy. Okay, and wrote this, the Clausius relationship. Usually, thermodynamic people say that the QE, the amount of heat coming from the surrounding, is always higher, or no, sorry, it's different. Should be lower. Probably they wrote higher or lower. Do you remember minor than or bigger than?
Bigger than.
But, okay, so we have to write. in this way. T, the S, the temperature, time, the variation of entropy is always bigger than or equal to dq, where dq is the amount of heat coming from the boundary. Okay, this refers to closed or open? Closed. Good. So we have QE, okay, the entropy and temperature of our system. So we introduce heat and entropy and temperature changes. And the relationships say that always T delta S is bigger than dq, dqe, okay? But I would like to write this relationship without the disequality sign. I prefer to write the equality. Therefore, T ds equal to dqe. Then I have to write something else here, plus something that I can call like P Greek, that is an amount of entropy production. Okay? This quantity has to be always positive or equal to 0 in the ideal case. It is the entropy production. Okay? So, being higher than 0, this way to write the second law of thermodynamics is equal to this one. Okay? Now, do you remember how the entropy can be product? Why we have a production of entropy? There are many different mechanisms. First, friction, LW. Okay. There are other mechanisms.
Due to irreversibility.
Sorry?
Due to irreversibility.
Yeah. A system can be irreversible only because you have friction or because you have other things. Remember the heat exchange. My colleague said that in order to have a reversible heat exchange, the heat exchange has to be between body having a temperature difference that is that approaches to 0. So when you have two bodies that exchange heat, in order to have a reversible heat exchange, the temperature of this has to be only a little bit bigger than the temperature of this. Has to be infinitesimal. So when you have heat exchange between body at the different temperature, you are introducing a mechanism of no reversibility. So you are producing entropy. So heat exchange with ΔT approaching to 0. There are other mechanisms. Are there other mechanisms? Probably my colleague said that the entropy is related to a property of the universe. The order. Do you remember? They say that when you have something that is really ordered, the entropy has to be very low. So by putting in order, you are increasing the entropy because the system is going to have low entropy. But doesn't mind. Another mechanism of production of entropy is to separate your fluids. When you have smoke here, air here, the system is going to be a mixture. Is moving but let me say another mechanism is this gradient in concentration. There are a lot of mechanisms, okay? But when we work with our machine, the most important mechanism is this one. So in our machine, we can say, okay, my problem, T ds, is equal to dQe plus the many type of irreversibility production, but the most important is del W. So the other one can be neglected, and this equal become about. Okay, so this will be the shape of our second law of thermodynamics in our machine, because we are working with machine where the other mechanisms are not important. In turbine, compressors, the most important entropy source is the friction. Wow, this relationship is very interesting because look and look. It's the same. So yesterday we obtained this relationship by combining our first law relationships that say, very important, it does not mind how you provide heat to your system. It's important the total amount of it. It coming from the surrounding and it coming inside, because this heat is able to change the properties of your fluid, to change the state. Today, thanks to the second law of thermodynamics, we have another interesting relationship that say that quantity, the Q, equal to dQe plus dLW, is also equal to T ds. And remember, yesterday we gave a definition for T ds. Sorry, a definition for the Q. We said that Q can be defined like by introducing this specific heat. This is equal to do you remember the definition of the specific heat? It was not the U. This is the specific heat. Does not mind if this heat is provided at constant pressure, constant volume. No. In a generic process, is always the variation, or better, the amount of heat that we have to provide in order to increase the temperature of 1 kilogram of 1 Celsius degree. It's not defined the process. Then we have Cp, specific heat at constant pressure. Cv, specific heat at constant volume. C is the specific heat. It does not mind the type of process. And this can be written like C dt. So at the end we have a relationship between C dt and T ds. This will be very, very, very useful. Okay, do you have any question about this? Okay, before to use this relationship, I would like to remember some useful relationship for our fluid. Okay? When we have to make calculation, we have to use a relationship that models the behavior of our fluid. We have many type of models. Depends of the fluid, depends of the working condition. Okay? The most popular model, the model that you used in the past probably, that we can use also today, but in particular condition, is the model of the ideal gas. Okay, are you able to give me an idea of this model? What does it say? How do you define the model of an ideal gas? First of all, you need a state equation for your gas. Do you remember the state equation? I'm sure you remember. P. V, which one? Specific volume? Specific volume. Equal to? RT. Okay. What is R? Oh, okay. So R is the gas constant, you say, okay. It is related to the universal gas constant. Do you remember? R0 divided by? Perfect. The value of R0? 8314. Unit of measurement? No. 8,000 is 4 Kelvin. Okay. And do you remember the value of R for air? No, but R. 287. Unit of measurement? No. When you divide by mole mu is kilogram for mole. Therefore, A is joule per kilogram Kelvin. Okay, this is for air. Obviously, this is constant for all gases. This value is only for our air. By changing the air, by changing the gas, we have to change R. Perfect. But do you think that it is enough? Or you have to give other? No, in order to define the ideal gas model. Well, we have to provide information about Cp and Cv. In an ideal gas model, Cp and Cv are constant quantity. Okay? And what kind of a relationship exists between R, Cp and Cv? Perfect. R is equal to Cp minus Cv. And obviously also this is constant. Okay? No, R is Cp minus Cv. That's the difference between them. Okay? This is the idea of the gas model. Sorry. It's the model of the ideal gas. when the temperature changes a lot, this approximation, Cp and Cv to be constant, are not so good. It means that when we are working with the machine, like for example an internal combustion engine, to say that Cp and Cv are constant is a rough approximation. So we introduce a big error in our calculation, because in that case the temperature changes from the environment temperature, 200 Kelvin, up to 100, 500, or sometimes 1500, sometimes 200 Kelvin. In this range, Cp and Cv changes a lot. Therefore, in this case, when we work with these machines, not in this course, but we use mean values, but the more accurate calculation can be done by using the model of a quasi-ideal gas. The model of a quasi-ideal gas say, like before, PV equal to RT, exactly like before, but Cp and Cv are not constant quantity, they changes with temperature, also for Cv. Okay, so we have to provide the relationship of Cp and Cv as a function of temperature. In other words, we have to work with the value of Cp and Cv that changes with temperature, or mean value in the range of temperature of our machines, that are quite different. And at the end, always we have that R equal to Cp minus Cv is not a function of temperature, but in this model has to be constant. Okay? Yeah, because I put mole here, not kilogram. You put it also 8.3, but with reference to kilogram mole. I wrote kilogram for mole, but it doesn't matter. We don't use this number, don't worry. We only use R. Okay? So that is for chemistry. We use always R. Another model that we have to use is the model of the real gas. Okay, in the model of real gas means that we cannot use PV equal to RT. When, for example, you probably used in the past something different than this relationship, or better, my colleague said, sorry, we cannot use this relationship. When? Do you remember? Mollier diagram. When you use the Mollier diagram? Where you are working with steam, with vapor. Means that when your gas is near to the condensing region, so is near to change the state, in that condition, you cannot apply PV equal to RT, because it's a very, very bad approximation. So in that case, for real gas, you can find the definition of a new thermodynamic property, that is PV over RT. So if you look this quantity, immediately you understand when zeta is approximately equal to 1, means that your gas can be modeled like an ideal one, as approximately ideal. But when Z is different than 1, you cannot use that model. Okay? Well, there are a lot of many diagrams that give you the value of zeta with reference to pressure and temperature. It means that if you are working with, for example, a machine with strange gases, helium at very low temperature or high pressure, you have to say, okay, I have to use this gas. I can write the relationship for an ideal gas. First of all, I evaluate zeta. I go in these tables, I read for helium the value of zeta, and I say, okay, it is approximately near to 1. I can use the ideal model. Is different than 1? No, I cannot use that model. I need tables. I need Mollier diagrams for helium, Mollier diagrams for water or for other substance. Okay? So when we are working with a real gas, in our course, we will use the Mollier diagram. The Mollier diagrams are all the diagrams that show the entropy in the abscissa. Okay, all the diagram. For example, TS is a Mollier diagram. HS is a Mollier diagram. Conventionally, all the diagram with entropy in the abscissa takes the name of Mollier. No? Well, if you remember, in this diagram, you have the distinction between steam region, superheated region, liquid region. Do you remember?
Yes.
It has this shape. Well, this is the critical point. The same diagram in this picture, HS, show a different trend. Well, this is C. And it divides the region of our diagram in 3 areas. This area, this is the area of the superheated. That is here. The air here. Saturated vapor means that we have both water and vapor. That is this area. Then there is another region here, very, 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 very close to the limit curve, that is for liquid. Liquid. The green is not a good choice. Liquid. Liquid. Okay. Well, it's very important. I don't know if we have to do now or later. Let me think. We have to stop at
50.
24 minutes.
12, 15. 15. So we have enough. Okay. So ma che cazzo. Okay, now I would like to think, or better to draw a line in this diagram where we have our closed system that work at constant pressure that will be heated. At the beginning, we only have water. And I would like to follow this diagram by thinking what happened. Okay? At the beginning, this is the state of my water. Means, for example, 20 Celsius degree with a proper value of entropy. I'm sorry, but I don't remember. At environmental pressure, 1 bar. Okay? What happened when I provide heat to our system? Temperature increases. Therefore, in the liquid region, temperature increase. Up to this point, okay? At this point, this is a 1 bar. At this point, what happened in our... There is the first ball of steam, okay? And from this point, by introducing heat, this temperature stay constant. And the temperature here is equal to, being 1 bar, exactly 100 Celsius. Okay? Now, by introducing more and more heat, I'm able to transform our water at the liquid state in water at the vapor state. So I'm changing the amount of water, or better, the vapor in my system. Okay? When I will be here, the 100% of steam is present. Okay. And what happened now by introducing additional heat? Temperature increase. Okay. So we are moving from liquid, very, very near to the limit curve, to vapor, superheated vapor. Okay. This is a constant pressure transformation, constant pressure process. Well, are you able to see the heat in this diagram? Remember the relationship we wrote before. T ds equal to the QE plus the LW. So it is our dq. Okay, so the area under this plot say the amount of heat that we have to providing. In other words, this is the amount of heat that we have to provide in order to increase the temperature of water up to 100 Celsius degree, 393 Kelvin. Okay? Perfect. Oh, sorry. Then this amount of heat is the what is? Okay, but it take a name. Latent. Latent heat. Why it is called latent? Because we are providing heat, but the temperature does not change. So we are not able to see the amount of heat that is coming by reading the temperature. This is why it is called latent. Then, the other amount of heat required to obtain to our steam. So, we have the heat required in order to increase the temperature of the water up to 100 Celsius degree at 1 bar. Obviously, by changing the pressure, will be a different value of temperature. Then, an amount of heat that we call latent in order to vaporize our water, and a third amount of heat required in order to increase the temperature of our steam, of our vapor. Okay, in order to this latent heat, what kind of symbol you used? I used R, obviously. I'm sorry, I will use R. Okay? But in order to understand the amount of heat that we have to introduce in order to move from the lower saturated curve and the higher one, liquid and vapor, we have to introduce a new variable that take the name of steam or vapor quality. Okay. Do you remember the definition of the quality? X is the mass of vapor over the mass of the total mass. The mass of vapor plus the mass of liquid. So the curve, this curve has a x equal to 0. This 1. And then we have many other curves in the middle that are shape of this type. Okay?
What about the critical point? Is it one there?
Here, the critical point?
The quality is equal to 1?
No, the quality is in the middle. It doesn't mind. So you have a liquid in this side, and U is not defined. You can say that it's 1 or 0. You are in the critical. You cannot be in this curve. When you are over this point, you are in the gas region, the vapor region. So it's not important to have.
Depends on the phase.
Which phase?
And in the critical point, you say whether x can be 0 or 1.
It's not important because it's in a point that can be both. It's the conjunction between them. But we always work in this area. Okay? Okay, this diagram has to be plotted also in the HS diagram. So this is our liquid, this is our critical point, therefore you have that here you go in the curve, and now the curve, the constant temperature curve, now what kind of line is? Parabolas, a constant line, a straight line, it does not mind. Horizontal?
No.
No, horizontal.
I think
Is a linear line. Okay? It's a straight line. Then you have the liquid and vapor. So this curve is with x equal to 1. This part is x equal to 0. Are you able to see the heat also in this diagram, or are not able to see it? Think to our system. No, I have the weight, so constant pressure. Okay. What we can write? This is our system, okay? So, we have to apply a relationship in the Lagrangian on Eulerian form. Is it a steady state process or not a steady state process? The density continuously changes, therefore no steady state. So we have to apply the relationship for closed system. So dQE plus dLE equal to du plus dhz omega. Okay. Now, about the last term, we can say that we are considering a state without movement before and after. Therefore, this term equal to 0. Okay? About the work done by the external force. No work?
No work.
When you increase the volume, the plunger moves. So we have a constant force, P times A, and a displacement. So yesterday we said that this is equal to P delta V. Okay? So, if we increase the volume, this force, the external force, does a negative work. Because this is the direction of the displacement, this is the force, the external force. So we have to write minus here. Then we have, sorry, I wrote delta, is not correct because I'm considering infinitesimal. So dV. Okay? And also I wrote V because this relationship is written with reference to the unit mass, so specific it. Then we have dQe equal to du, then minus p dv becomes plus p dv. Well, but the pressure is constant, therefore we can add v dp, because this is equal to 0. But these two gave us dpv. And we know that U plus PV is our entropy. Therefore, dQe is equal to dH. So, we can say this is the amount of heat required in order to change the temperature of our water from the beginning to 100 Celsius degree. This is the what is this? The latent heat. That is the amount of heat that we have to provide in order to increase the temperature of our saturated vapor here to this value. So, the area in the previous diagram, this area becomes a segment. So in both diagrams we are able to understand the amount of heat provided in order to obtain our process. Okay? Now we have 10 minutes, okay? A very simple things. In the previous sketch, I analyzed a particular process that was a constant pressure process, okay? We can define many different types of processes. Some of that are particular elementary process, okay? So the type of process we wrote before, constant pressure process. Okay? Can you give me a list of other elementary process? Quindi, so this is isobaric, okay? Your colleague suggested isochoric. Then isothermal. Then okay, adiabatic. What is the property? But in the adiabatic nothing stay constant. Adiabatic is QE. Let me write here. QE equal to 0. Adiabatic. And sorry, QE different than 0?
What do you mean?
Diabatic. It's only a name. But here, other property that stay constant. Entropy constant. is another one. Polytropic. And what I have to write here? Constant.
And
It has to be a property, because here process that are something constant. Thermal, isothermal, temperature. Volume. In the polytropic, something has to be constant. That is a equation. It's not a property. Which one?
There is a coefficient.
Which one?
And like a
gamma
The exponential index, m, gamma, no.
CP or CP?
Near.
CP over CV.
No.
C. Just
C is constant. So in a polytropic process, we have that the specific heat is constant. C. Okay? Now, with reference to a gas, give me the thermodynamic relationship, the relationship between the properties. So, the equation. P constant is
V1 T over T1.
okay. This is the equation. For isochoric,
T over C.
PV over
For isochoric T over
for isothermal, for isentropic,
PV over isentropic.
PV at a power of,
And
okay, I will call it K,
yes.
where K is defined as
K.
K. K, the specific, the index of the isentropic. CP, CP over CV. Do you remember this value for A?
1.41.
No, 1.4.
1.4.
Okay. And a polytropic process,
PV and
PVM is constant. Okay. Now, Oofla. This relationship can be written like this one. So we can define a particular value of m for each one of this. Okay? Obviously, for PV equal to at m equal constant, the value of m is m. For the isentropic is k. But for the other one, for isothermal is 1. Perfect. For isobaric,
0. No, focus. Isobaric.
is 0, no? PV at 0 make P constant. Therefore, 0. And this one? Write P at the exponential 1 over m time V equal constant. Therefore, 1 over m has to be equal to 0. Therefore, the value of m has to be infinite. Okay. Now, we can also write the particular value of C for each of them. Obviously, when you are working with a constant pressure process, C is equal to CP. when we are working with an isochoric CV. When you are working with an isothermal, well, think to the thermodynamic relationship. Isothermal.
Internal energy becomes zero. So.
Write the relationship. We wrote C dt equal to dq. Do you remember? But dq also equal to T ds. Okay? So, we have isothermal. This is equal to 0. But this can be different than 0. Also this can be different than 0. The only way to have C delta T dt, a number that is different than 0, with the T equal to 0, is to have C approaching to infinity. C, obviously, this will be C, and it is related to M. You should remember this relationship, but doesn't mind. This is CV M minus K over M minus 1. Let me check. Yeah, okay. And in this case, for the isentropic, always follows, you have to follow this idea. For the isentropic, this is equal to 0. Sorry, not different. Equal to 0. But C dt can be different than 0. Therefore, C has to be 0. If you have 0 time a number different than 0, you always have 0. So, this is 0. Okay? Now we stop. Then, I would like to show you how this table is very, very useful in order to understand in your diagram the shape of your process, to understand the type of relationship you have to apply. Okay? So we stop. Okay, please. Okay, this was the table that we derived a few minutes ago. Okay, now I would like to analyze how the function, the process in our TS diagram changes by changes M, the polytropic index. So, think to your TS diagram. Obviously, you can say that this one is a what kind of process? Isothermal process. And this one will be an isentropic. Okay. Then we have also isobaric and isochoric. Oops, sorry. Okay. This one is the isobaric, and this one is isochoric. Okay. Now try to put our M index on this process on these lines. We have that for an isoentropic, we have K, isochoric, infinite. So M is equal to K here, infinite here, then isobaric and isothermal. Isobaric is 0, isothermal is 1. Okay. Therefore, you have 0 also here, infinite here. Infinite here. So, look, 0, 1, a little bit higher than 1, for A 1.4, infinite. At the same time, 0, 1, K, infinite. It means that this region is the region where M is positive. But it exists also a region where M is negative. Because remember that M is only an exponent, has no meaning, then a mathematical meaning. And also you can say that a process of this type, horrible, let me change code. Okay. A process of this type, so with a slope of that moves from 1 to 2, is a polytropic process with an M between 1 and K, so lower than K. At the same time, blue change color with violet. A process like this is a polytropic process with M higher than K. So, if you remember, when my colleague studied a turbine, better, sorry. What kind of thermodynamic process he drew? You remember? Okay, this is isentropic when QE, for example, is equal to 0 and LW is equal to 0, ideal expansion. Okay, but generally speaking, our turbines are adiabatic because they, okay, but LW is different than 0, the real case. The process will be a process like one, the black one, or like the violet one.
Violet, it's more vertical.
Okay, you suggested.
More vertical.
No. You suggested it. Okay? True. Let me do. because unfortunately your memory is not fantastic. But we can understand that it is wrong. Because no, this is our process. Do you agree? The area under our process, by applying the second law of thermodynamics, is equal to QE plus LW. Okay? But in our problem, an adiabatic turbine, QE is equal to, therefore, this area is our LW. But is it positive or negative? Is negative. But LW can be negative? No. It means that this is wrong, because it is related to an adiabatic machine with a negative, so a cooling effect of your friction. It's not real. The thermodynamic process in your turbine has to be of this type, where this area obviously is always QE plus LW, thanks to the second law of thermodynamics. QE is equal to 0 and LW is positive. This is okay. So in our turbine, M is lower than K. Yes, is lower than K. Compressor. Our motor 1, 2, 2. Now the pressure in our compressor, this is T, increases. Okay? Always consider an adiabatic machine, but real. Our process will be of the type 1, 2 black, or 1, 2, 2, 1 black, or 1, 2 violet. Which one? The violet? Try with the other one, okay? Like before. For example, we are thinking to a process of this type. 1, 2, 2. So, with M between 1 and K. The area is, as usual, QE plus LW. QE is equal to 0. And LW is positive or negative? Another time is negative, because T in the S is negative. You are moving in the negative direction of S. So, not possible. Your process has to be of this type. One, two. Now the area will be our LW equal to T in delta S, but delta S is positive, therefore it is congruent. So our compressor has to be represented with a line of this type, with M higher than K. Our turbines, the expansion in our adiabatic turbine has to be of this type. I'm sorry, when we have a real but